So up until this point, we've talked about Newton's laws in circular motion for uniform circular motion. That is, the speed of our object around the circle is exactly the same. This worked well for horizontal circles, a car going around a track, even when we had the yo-yo, as long as it was horizontal along the surface. The F equals ma, where a is just equal to the centripetal acceleration, allowed us to solve the problem very straightforwardly. But now we're going to see how things change if we don't have uniform circular motion, but non-uniform circular motion. Specifically, what if we're speeding up and slowing down? How tough does the problem become? Well, one type of circular motion that is very clearly non-uniform is vertical motion. It's not impossible to have vertical uniform circular motion, but it is a lot harder because as an object goes around in a circle, like so, you'll see that the forces on it are going to change at various points around the circle. If I was to stop this at some point just to look at the forces on it, let's take a look. So, hold that there. So I'm going around, I stop right here. So let's say that yo-yo was on its way up right at that position. What are the forces on the yo-yo itself? Well, we know there's a tension force along the string and it's pointing away from the yo-yo, so towards the center. And I've got a force of gravity straight down. Can you think of anything else? No, I don't think so. But look how that changes over here. When I draw the forces on my yo-yo when it's at the top of its circle, now the force of gravity and the tension are actually in the same direction. And it continues. Here they're perpendicular. And here you've got force of gravity down and tension up. And so as this object goes around, it's going to have different forces at different points, and probably you're going to have non-uniform circular motion. It's unlikely that the speed is constant the whole time during this specific kind of vertical motion. And so when I talk about forces in non-uniform circular motion, I'm most interested to see what happens for vertical circles. Let's take a look. So this is forces in non-uniform circular motion. And so the question is, how do things change compared to what we've learned up until this point? What happens when speed changes? Now, not only are the forces on our object in a vertical circle going to be different at every point around the circle, but I'm a little worried about the acceleration as well. Usually we say acceleration is just equal to centripetal acceleration, but now we're going to have an acceleration that has to do with speeding up and slowing down as well. Let's not go that far yet. Let's start by asking ourselves, what are the forces on an object traveling around a vertical circle? All right, and we will do the example that we just talked about. That is a yo-yo. And so once again, for our yo-yo, we're going to think of it as a mass on a string. So there it is at its very top of its motion, and it's going to undergo a perfect circle. Let's see, 1, 2, 3. And end up right there, and then continue on up. Should be a perfect circle. All right. Here is the center of our circle. I want you to think of this, of course, as a vertical. It's not an overhead view. You're looking at this kind of sideways. And let's draw, again, the free body diagram of the yo-yo at the very, very top and at the bottom. And so at the top of the circle, it's going to look like this. I've got my mass there. And we have our force of gravity down, of course. Force of gravity is always down. That's an easy one. But clearly it's attached to a string. And the tension should be along the string, as it always is, and away from our mass. And so tension should also be down. They don't have to be equal or anything like that, but they're both in the same direction. Now that's a little bit surprising to me, because as this mass goes around a vertical circle, it doesn't fall. If both of the forces on this yo-yo at the very top are downwards, shouldn't it fall? Yet it doesn't. It goes around and continues on. Are both of those things possible? Can you have all of the forces pointing in a certain direction, yet its motion is going perpendicular to that, those forces? Yes, it's absolutely possible, because remember, it's the acceleration that is affected by the forces, not the direction of motion or the velocity instantaneously. And so it's a matter of time before it would affect it. When would it affect it? Well, let's see what happens when I go around this circle slowly. So I'm going to try to go around the top very slowly. So every time it gets to the top, it falls down again. Intriguing, intriguing. So the forces here are affecting its motion, and it's coming straight down. But if I go faster, if I go fast enough, then it looks like I'm actually able to get around without having any problems with the fact that both of the forces at the very top of the circle are pointing downwards. And so we see that right there. Okay, great. So now do me a favor and draw the forces at the bottom of our motion. In fact, it's pretty easy. The bottom is actually quite easy, because as we see here, again, the force of gravity is going to be down as always, but this time tension is straight up. And so at the bottom of the circle, our free body diagram looks like the following. We've got the force of gravity downwards, and we've got tension upwards. Okay, very interesting. It seems to make sense for the yo-yo, but tension is always a little bit easier to see, isn't it? Let's do an example where we don't have a string that's forcing us to go along this vertical circle. Let's think of a vertical circle you can make without tension. Let's do an airplane. So some kind of a fighter jet or some other kind of airplane can actually do what's called a loop-de-loop. That's the scientific name for it. A loop-de-loop is a full circle around, right? So the airplane goes this way, then it climbs up, and then it's upside down before going around again. And it could be a tight circle, or it could be a very, very large circle. There's an airplane that will be able to achieve near weightlessness, that is an acceleration downwards of 0, by doing this exact move that we're talking about. Its nickname is the Vomit Comet. Feel free to look at that, and it's a way of simulating 0 G's without having to end up in orbit or beyond. But we're just going to talk about a simple airplane probably a fighter jet, something like that, that's going to do the classic loop-de-loop. And so let's say that our airplane is headed in this direction. And it's going to do this full circle, end up there, and come back down again. And at the top, let me draw this airplane upside down. Pretty good, pretty good. And so those are supposed to be right on top of each other. Let me move it just slightly. Okay, good enough. So we've got ourselves another vertical circle, this time no string. And I want to know what the forces are, not on the airplane, you'll see. So this is a loop, de-loop, I think that's the spelling. Let's clear this up a little bit. There we go. Not on the airplane itself, but what about if we had ourselves a fighter pilot? A fighter pilot is sitting in the cockpit on the seat and is going to experience different forces at the top and the bottom of the circle. So I'd like you to try this yourself. I'm going to draw a bit more of a realistic picture just so we understand what we're drawing, but I would like you to draw the forces onto our pilot. And so here is a picture of our pilot sitting. Flying the airplane. Those arms are weird. Let's say like that. There we go. And the same pilot is going to be up here at the top of our loop-de-loop. All right, and we're going to make things extra interesting here. Let's say that the pilot is not wearing a seatbelt. That's right, the pilot is not wearing a seatbelt. And let's also have it so that she doesn't fall out of her seat, okay? So she's going to stay in her seat here at the bottom. Obviously, that's not a big deal. But even up here, despite not having a seatbelt on, she's not going to fall off of her seat and onto the glass part above her. She's just going to go through that rotation. So right now, draw me the forces on our pilot. So you see it over there. Might as well start with the one at the bottom. That one is a bit easier to do. And so the forces on this pilot are going to be, of course, as usual, force of gravity down. So this is just on the person, force of gravity. And another force is the normal force. She's sitting on the seat, and so there should be a normal force in the equal and opposite direction, giving us those two forces. Now, what are the forces on her at the top of the circle? Assuming she's going fast, right? As we saw with our yo-yo, you have to have a fast enough speed to make it over the top. So she's not going so slow that she's going to fall. I'm not talking about the airplane, but the pilot herself. She's going fast enough that she will go around the full circle. And so what that means is you're still going to have the force of gravity downwards. And there's one more force. It is also the normal force. She's still sitting on the chair. And so the normal force is also downwards. It's a little bit shocking that all of the forces on her are downwards, yet she doesn't fall. All of the forces on our yo-yo are downwards, but the yo-yo doesn't fall, as long as the yo-yo is going fast enough. And as long as the pilot is taking the loop fast enough, she will also not fall. Where else do we see this kind of example? Well, you could do an experiment with a bucket and put something in the bucket. I've got a simplified version here for our video. This is a water bottle, and you can hear that the bottle is full of water. And so what are we going to do? Let's see what happens to the water when the water bottle undergoes a vertical circle. If I go slow enough, you hear that it falls down. I want you to think of the bottle as the airplane. I want you to think of the water as the pilot. Even if our bottle makes the full circle, if it's going too slow, the water will fall downwards. Gravity and the normal force will have enough time to push it down. But if we take this circle fast, let's see what happens to the water. Nothing. You only heard a splash at the end when I stopped, but if I do a full circle, one more time, as long as I go fast enough, the water stays up here. The water is pushing up against this container. So force of gravity is down. The normal force is down as well. They're both pushing down onto our water, but because it's going fast enough, it can make it around the circle. Too slow, it'll splash down. Fast enough, no problem. Okay. Okay, so that's good. Let me just get this out of the way. Wait, what's that you say? You want me to try it without the lid on? I mean, that's a bit riskier, but let's see what happens. Okay, so let's see if I go fast enough that the water is not going to fall on me. All right, ready? Here we go. Okay, yeah, no problem. I went fast enough, and again, it was able to go around. We don't want to go too slow, otherwise, just kidding. All right, so what do we have? We have our free body diagram, and what we realize is the free body diagram changes throughout our vertical circle. So for a vertical circle, or in this case, non-uniform circular motion, the free body diagram is going to change at every point around our circle. Gravity is always going to be pointing downwards, while our normal force, we will see, will always be pointing towards the center of the circle. And so where do we actually do these problems? How do we handle the fact that the free body diagram looks different at the different locations? Well, you simply do it at the most interesting part. And so all of the non-uniform circular motion Newton's laws problems occur at the very top of the circle or at the bottom of the circle. Those are the two most interesting places, and they allow us to find things like the minimum velocity necessary to go over the circle, or if we were, let's say, on the outside of a circle, the maximum velocity we can go over a circle, say the bump on a road or something, without leaving the circle. And so we'll see lots of examples of that. So let's write that the most interesting point is at the top of the circle. Specifically at that point, you have the conditions, the maximum conditions to stop your circular motion. That's where you feel the most forces that want you to fall. And so most interesting point is at the top of a vertical circle. Where we, and we're just about to do this, can calculate the minimum speed needed needed to make it over the loop. Let's say to make it around the loop. Around or over, they're both good. Okay, so let's try this problem out. It says that Wonderland, and for those that don't know, that's Canada's Wonderland, the biggest theme park in Canada. And every year, not every year, but often they come up with brand new gigantic roller coasters. And so in this particular example, Wonderland is designing a new roller coaster. The radius of the upside down loop is going to be 22 meters. So what is the minimum speed necessary for the coaster to make it around the loop? Okay, this is great. This is super important information. So we're going to have ourselves a loop in a roller coaster. Everyone knows what a roller coaster is. It's like a little train. It goes around, it goes up, it goes down. And then sometimes the roller coaster goes upside down. They do a complete loop. And it's super, super scary. I'm not a big fan of upside down roller coasters, but I want to make sure that they're going fast enough that they can go over the circle without falling downwards. If our roller coaster goes too slow to the top, the cars or the people will fall downwards, assuming they're not attached to the tracks in some way, or wearing seatbelts, etc. So the question is, how fast do we have to go to be able to go around that loop? And the only thing they give us is the radius of the loop. So it seems like you don't have that much information, but I think we're going to be able to figure it out. All right, so if we want to get around a roller coaster loop, the place we have to make sure we can make it past is the very top. At the very top, the forces are in such a direction that we maximize our forces that would drag the roller coaster down. And so we only have to look at what's happening at the very top of our roller coaster. And so let's say that this is our car, the roller coaster train or car, and it's at the very top of the roller coaster now. And we want to know what the forces on that train car are. So go ahead and draw them. In fact, it's exactly the same as it was for our pilot. You've got your force of gravity downwards. You've got your normal force also downwards. Again, remember that the normal force is perpendicular to any surface. And so even if we're on something that's kind of up here, the normal force is going to be pointing downwards. All right, so here we go. Let's go ahead and apply our Newton's laws and see what happens. So we'll use a sum of the forces in the y direction. We need to give our y a direction as well. Let's make plus y downwards. We have the force N downwards, we have the force of gravity downwards, and all of those are equal to mass times acceleration. Now it's acceleration in general, and in general it's a combination of both centripetal and tangential. But we're only going to worry about the centripetal acceleration. We're going to assume in this case that at the top of our slope that the roller coaster is powered by whatever powers the roller coaster, electricity or whatever. And so we're going to have a constant speed here. And so in this problem, it is okay to use a centripetal acceleration. You'll always use a centripetal acceleration as opposed to a total acceleration for these types of simple problems. Okay, so taking our N plus Fg, which we know is mg, and our mass times centripetal acceleration, which we know is v squared over r, we can begin to think about how fast we go to make it over this circle. Now, if we go really, really, really fast, like way faster than we need to go, what force is going to increase? Well, the force of gravity is not going to change. It's the normal force that increases. The same thing happens with this yo-yo. The faster I go, I'm going super fast right now, I can feel the tension in the string. The tension in the string is getting stronger. And so in this roller coaster, what's happening is the normal force down gets stronger. And you know this, right? Like if you're going in a ride at an amusement park and you're spinning around really, really fast, you get kind of like pushed up. You get pushed up against the seat. And so the normal force gets stronger and stronger the faster you go. But we're not asking you to find any old velocity at some normal. We could do that. I could give you the normal force and you could calculate the velocity, but that's not what this question is asking. It's asking for the minimum velocity necessary to make it over the circle. So we always make sure we go faster than that. Well then, let's think about the minimum velocity necessary to make this yo-yo go around, all right? I'm going to slow it down. I'm going to slow it down, slow it down, slow it down until it can't make it over. So there is a velocity, not that one, where it just makes it over. What is the tension in the string when this yo-yo is at its minimum velocity necessary to make it over and around again? What is the tension on the string if the yo-yo is going as slow as it can possibly go, but still make it around the circle? Answer me that question. That's right, it's zero. The normal, the tension is zero. I hope I said tension and not normal force there. I meant the tension is zero. And similarly, we can do the same problem for the pilot doing the loop-de-loop, or the water that's located in this water bottle. And so we have ourselves a water bottle full of water, and we want to go around in a circle without it splashing down. That was too fast. I know when I went super fast like that, the water here is pushing up against here, and there's a large normal force. Okay, let me go slow. Okay, I went too slow, it fell down. I want to find that perfect balance where I can make it around the circle, but I'm not pushing up against the ground. Here we go. Oh yeah, that was it. That was it. Found it. And so at that velocity, the normal force on our water, the normal force on our pilot, the normal force on the roller coaster is zero. Zero. That's how we calculate the minimum speed, and that's how we maximize the fun. The reason roller coasters are so fun is when you are at various points, They want it to feel like you're leaving your seat. You get that sensation? Sometimes it's at the top of a circle. Sometimes it's at the, let me repeat that. Sometimes it's at the top of a hill, and sometimes it's at the top of a circle, the loop that we're doing right here. And so regardless, we have a normal force equal to 0. We will be able to find our minimum velocity where n equals 0. And that's going to make our equation very much easier. mg is therefore equal to mv squared over r, where v is our minimum velocity necessary to go through the loop with a radius of r. The mass of the roller coaster doesn't matter. I mean, it matters to generate the velocity in a more engineering kind of way, but it doesn't matter for how fast you have to go to not fall. It's only dependent on the radius. Fascinating. And so we can calculate the minimum velocity as just g times r rooted. Cool. So it only has to do with the radius of our loop and the acceleration due to gravity. And so let's actually get a value here. The minimum value is 9.8 times 22 all square rooted gives us a value of, throw that into your calculators, 15 meters per second. That's it. You can convert that into kilometers an hour if you want to see what it is, understand that value a little bit better. But that's how you would calculate the minimum velocity necessary to go over, or I should say go through a loop without falling down. Any velocity above that will work as well, but then you would start to accumulate a normal force. And the normal force gets stronger and stronger the faster you go. So the last thing that we want to look at is the concept of angular momentum. We have dealt with linear kinematics, linear forces, linear momentum, and linear energy. Of course, we didn't talk about those things with the word linear in front of them, but now that we've started to explore rotational concepts in physics, we've done rotational kinematics and forces in rotational motion. And so the next natural thing is to talk about rotational momentum, which is commonly referred to as angular momentum. And you can imagine what angular momentum is fairly easily by conceptualizing the idea of momentum itself. We've talked about momentum as this combination of mass and velocity. So the faster something goes, the more massive it is, the more momentum it has. Now, if my object is not moving with some linear velocity, but in fact spinning around, so we have some object spinning around, well then, I suppose if I spin faster, then I will have a greater angular momentum. That is true. And so it looks like it needs to be some kind of combination of mass with some kind of an angular or rotational velocity. That's essentially what it is, with one additional difficulty to it. We're going to introduce angular momentum now as capital letter L. And angular momentum is a vector, and let's call it the rotational version or analog of our regular momentum, P. And so I want to, first of all, see how those two terms are related to each other. Because remember that P is equal to mass times velocity. And we also have that V equals omega times R. And so that's going to help us get to the point where we can put those together to come up with an equation for our angular momentum. Let's see what it might be. So instead of L, I have instead of P, I have L. And instead of omega, I'm going to have, instead of v, I'm going to have omega. What about m? Should m stay the same, or is it possible that m has a rotational analog as well? One might consider just doing that and hoping that it works out, but that would be incorrect. Our rotational momentum is not mass times omega. It's a little more complicated than that. Let me explain to you why this is not good enough. Let's say that I have an object that has a mass. Say a swimmer, right? A diver, in fact, a diver. So let's consider the Olympics, platform diving. Our diver is at the very, very top of the dive, and they jump off of the diving board. And usually when they jump off, they're nice and long and lean, and they're jumping off, and eventually they go into like this little tuck. They go into this little roll. And so at those two locations, being straight and being curled up, we see that the angular velocity actually changes. And the reason the angular velocity changes has to do with the fact that even though the mass stays the same when the swimmer is straight or when the swimmer is curled up, where their mass is located actually makes a difference. Not only is mass important here, but so is the location of that mass. And that mass or location of the mass is called I. And I is the rotational analog of mass. It's also known as the moment of inertia. Moment of inertia is a combination of the mass and where the mass is located. What it basically means is knowing the mass of something and knowing how fast it's spinning around is not good enough to figure out what its angular momentum is. You have to know where the mass is compared to the rotation axis. So for example, if I'm standing completely still like this and I'm twirling around, I'll have a smaller angular momentum than if I spread my mass out. So I still have the same m, but because I'm spreading my mass out, now suddenly my moment of inertia has increased. And now if I spin around, well, if I'm spinning around at the same speed, then I'm going to have a higher angular momentum. So I has to be dependent on both the mass as well as where the mass is. All right. And so unfortunately for time reasons, we're not going to get into playing with the equations for the moment of inertia. And so I'm just going to write them down. So if you have a bunch of point masses and you want to calculate their moment of inertia, it's just a combination of the mass themselves multiplied by how far away from the rotation axes that mass is. And so if you just have one mass, it would be mass times r squared. But if you have a whole bunch of them, then you just add them up. The sum, like so. Now, more interestingly than talking about the angular momentum of a point, you want to talk about the angular momentum of a mass distribution, something that actually has a size to it, and you can do that as well. Let me mention that this r here is the distance from the rotation axis to the mass. And we can figure out what the moment of inertia is for some object through the very, very general equation of the moment of inertia is equal to r squared, the integral of r squared dm. We will not be using that due to time limitations, but it's just there for your notes. What we often end up doing is using a formula instead that gives us the moment of inertia of a specific body. So for example, let's say usually we don't calculate moment of inertia for simple shapes like a sphere in this particular class. But rather look it up. And so, for example, we can do a sphere. And for this object, we also need to know where the rotation axis is for us to look up the correct equation. So let's pretend we have a sphere with a rotation axis through its center. In that case, you can look up or do the integral to get a value of 2/5 mr squared, where m is the mass of our sphere and r is the radius of the sphere. And so it'd be like kind of having this sphere right here that is rotating about some center axes like that. Okay, so that's how you would calculate the moment of inertia if you were to do that sort of thing. But what I really want to talk about is the angular momentum. How do we actually use the angular momentum? Well, just like linear momentum, no one actually cares what the angular momentum is. No one is looking for the angular momentum of an object to try to understand the object. What we care about is, of course, conservation of angular momentum. And so conservation of linear momentum was really, really useful when we had objects that collided together and then either stuck together or separated, etc., to get our unknown values for velocity or mass, etc. Now, we're not going to talk about collisions so much as we realize that now an object, a single object, can have a conservation of momentum. Recall that there is nothing useful about saying P initial equals P final for an object with a constant mass, because then velocity is constant as well. Now remember that these conservation equations only occur when our net forces are equal to 0. And so the same thing is going to happen with angular momentum, but conservation of angular momentum actually occurs even for a single object. Let's take a look. And so in this example, we have a figure skater who is about to go into a fast spin. And she is not going to add any additional force or torque into her spin. All she's going to do is change her moment of inertia by bringing her arms and her legs closer to her body. And notice how the spinning increases. So This is one object with one mass, but a change in moment of inertia. Here we go. So she goes into spin, arms out, legs out, and she brings them in closer and closer and closer, and Natalia achieves a record of 308 RPM. So she's able to spin, apparently at a world record pace, because she manipulated her own moment of inertia to increase the velocity, the angular velocity. One more time, let's watch it from the start. So very slow, nothing much is happening, goes into the spin. Not too quick, but as her arms and her legs come closer and closer to her body, she gets faster and faster and faster. She's manipulating her moment of inertia to increase her angular velocity. It's done through the following equation. L initial equals L final. This is true for multiple objects. If you had a bunch of spinning objects and they hit each other, maybe like a spinning record and another spinning record falls onto it, yes, the angular momentum is conserved. But for one object, it's also conserved because this time we have the ability to change our moment of inertia for a single object, especially an object that is an extended body that can manipulate itself like a human being. So for one object, our conservation of momentum equation looks like this, and it's fantastic. It's fantastic. It's what allows the speeding up and slowing down by essentially the motion of our arms and our legs, of taking different amounts of mass and distributing it differently. So we saw some examples of that already. We see that with a figure skater. Notice the figure skater didn't increase her speed by like pumping. She wasn't adding torque or forces into her spin. All she did was move her eye from a very, very high moment of inertia to a low moment of inertia, making her velocity change from a low angular velocity to a high angular velocity. And we have the same thing happens in ballet, gymnastics, diving. There's so many examples of it. You ever see those skiers? They go off the jumps and then do all those tricks in the air. That's another really, really good example of it. Another great example of it is gas clouds. A little less obvious, but this is super, super important in the development of many astronomical objects, is large gas clouds that are spinning very slowly, collapsing into much, much smaller disks of gas that are spinning quite quickly and eventually forming new and interesting things. And so let's do a quick example of this with Natalia from the video. Let's say that Natalia obtains the world record for speed figure skating spinning, if that's a thing, for speed spinning. Let's just write that. Speed spinning as a skater by spinning at 308 RPM. Now she does this by altering her moment of inertia from 1,150 kilogram meter squared, that's the unit of moment of inertia, to 225 kilogram meter squared. So she goes from a high moment of inertia to a low moment of inertia. The question is, what is her initial speed? So we have her final speed of 308 RPM, that is angular velocity. We have her initial inertia of 1150 and her final inertia of 225. Can we calculate her initial speed? And you know what? Let's do it in RPM just to make things a little easier for us. Since it's originally in RPM, we're actually going to be able to keep it in RPM because all we have is that L initial equals L final, or the initial moment of inertia times the initial angular velocity equals the final moment of inertia times the final angular velocity. We're looking for our initial value, and so it's just a ratio of final moment versus initial moment multiplied by our final angular velocity. And since this ratio is unitless, because you have the same units for them, then we can keep our RPM to get our final answer in RPM as well. We've got 225 divided by 1,150, all multiplied by 308 RPM. And since we're in RPM, we can stay in RPM by multiplying by that ratio, that unitless ratio, giving us an initial velocity of 60.3 RPM.